Welcome back to AP Calculus AB. We're on day 63 today, which is a really easy continuation of what we did last class. Just a quick reminder, last class we were introduced to the idea of an antiderivative, and we put that plus C at the end to show the full, we call them a class of antiderivatives. And we also learned what this cool elongated S is. That's our integral symbol. And we discussed how an integral symbol is always matched up with this dx part at the end. It's called a differential. And they kind of sandwich between the integrand, the function inside the integral, that tell us what we're trying to find the antiderivative of. So there are 4 warm-up questions here, and I'm going to say be very careful. They're a little bit trickier than last class. They bring in some trig functions. They all have to do with trig functions as a heads up. And you're really going to want to make sure that when you take the derivative matches up to what you started with. They're in no particular order. I wouldn't say any one is harder than any other. Maybe 4 is the trickiest, but it's not necessarily the hardest. So why don't you take the next minute or two, pause this video, try the opener, and then we'll come back together and see how you did. Ready, set, go. All right, and you're back. Strangely, 1 is probably the hardest for someone that hasn't done calculus in a while, but should be the easiest for you. And the reason it should be the easiest for you is because you've been keeping up on your independent practice, and the 20 or so times that I asked you last semester and last night to fill in our antiderivatives in a chart kind of like this. Hopefully you did it so that you have all these memorized, and you know that the antiderivative of secant squared is tangent of x. Why is it tangent of x? Well, if I wanted to check it really quickly, if I asked you to take the derivative of tangent of x, you should know that that is secant squared of x. Right? We're not going through the process of how to find that. You just need to know the derivative of tangent is secant squared. And if you know that, then you know the antiderivative of secant squared is tangent. And although we were able to find a way to take the derivative of tangent, right, it is sine over cosine and use the quotient rule, you will not, I think, be able to find a way to find the antiderivative of secant squared, at least not easily. So this is one you just have to know. 2 and 3, though, add a little bit more logic. And it's interesting because looking at 2 and 3, you might think they're a little bit easier than 1. And I would argue that maybe they're not. So let's look at problem 2. Okay. Problem 2, you're probably going to be tempted to say that this is something like cosine of 3x plus c. And you could be right. How do we know if you're right? Well, we of course test it. So let's see what happens if we take the derivative of that cosine of 3x, and I'm going to leave out the plus c because that goes to 0. Well, a couple things. First, the derivative of cosine is negative sine, isn't it? And that already doesn't match what we started. There's no negative over there. So you might say, well, okay, I think we could fix that. Couldn't we just put an extra negative out front? Well, let's try that. So if this one didn't quite work, we made it a little bit better. And let's say, okay, what happens if we take the derivative of negative cosine of 3x? Well, the negative stays. The derivative of cosine is negative sine. And yeah, actually we're looking pretty good here because these become positive sine of 3x. But what am I forgetting that we shouldn't forget? Oh, that's right. Whenever you do the derivative, you need to invoke the chain rule. And so the derivative of negative cosine of 3x is negative sine of 3x times the derivative of the inside. So there's an extra 3 there. And so this becomes sine of 3x times 3, which certainly does not match what we started with. There is not an extra 3. So then the question becomes, well, wait, how do we cancel out an extra 3? Well, that's nothing too terrible. I can alter this just a little bit more. And I think if we put a negative 1/3 out front, then we're good to go. Right, that negative 1/3 is a constant that's multiplying, so we don't need the product rule or anything weird. And I think that will cause our antiderivative to match up with its original integrand. Let's try one more. In order to do this one, instead of thinking of it as cosine of x divided by 2, maybe think of it as cosine of 1/2 x dx. Because, of course, those are the same. And when we try that antiderivative, we say, okay, well, I think the antiderivative of cosine will work sideways this time, is going to be negative sine of 1/2 x. And then I won't forget the plus c, which I seem to have done on a few of these. No, I remember those. All right. So then we think, okay, well, let's take the derivative. So to check this, I'd say, well, we need the derivative of negative sine of 1/2 x. And that becomes negative cosine of 1/2 x times an extra 1/2. And let's see, does this match what we started with? Not quite. There's an extra negative, so we actually don't need a negative here. And then there's also an extra 1/2. So what cancels out that 1/2? Well, I think we need a 2 out front. And we're good to go. So although our derivative rules taught us that whenever you take the derivative of a function that starts with c, the answer is always negative, that is not true for antiderivatives. And there's no rules you need to remember here. Just try the antiderivative, quickly differentiate in your head, see if it matches. If it doesn't, then take the negative away or add the negative as needed. And that's that. So I think we have our final answer at the top. 1 to go. Now this one is a little bit trickier, and in order to do this one, we need to remember what happens when we're asked to take the antiderivative of 1 over 1 plus x squared. Well, hopefully we're thinking, wait, isn't that, you said there was trig, but I don't see trig here. Isn't that one of those weird inverse tangent or inverse sine ones? And yeah, it is. You do need to know both of those, and in fact, we need to remember that this is the inverse tangent or arctangent plus c. Now, this is a little bit trickier, though, because we don't have x up here. We have 2x. So we might think, okay, well, that's still pretty darn similar. Won't it just be the inverse tangent of 2x plus c? And the answer is almost. But if I were to take the derivative, right, we need to check again. Inverse tangent of 2x. This becomes 1 over 1 plus what was inside squared. But what have we not accounted for with regards to the derivative? And that's that extra 2x. That'd be multiplying by an extra 2. There's no extra 2 in this original problem. That's a 1 up here. So I think in order to account for that, we need a 1/2 that goes out front to cancel out the 2x when we do the derivative. All right. Well, I think for the rest of today, you're going to need a quick reminder about what all of your derivatives are. So why don't you go ahead and pause this again, fill in those 12 derivatives there, and then when you unpause, I'll quickly write them in for you if necessary. And then we have a couple more practice ones to do, and that's it for the day. Then you guys will have a little practice on your own. Ready, set, go. All right, hopefully the table that you see on the screen is the same that you ended up with. There's always a few tricky ones in there. I find students really struggle to remember these guys and these ones. Of course, these last two, these ones over here, are very, very uncommon on the AP exam. Maybe they show up once every other year. I'd argue, though, that recently these ones, the inverses, have shown up every year. And they're a pretty common antiderivative, or we'll get more into completing the square or some long division stuff that makes them pretty common problems. Maybe not common so much that they're every problem, but at least one problem every year seems to deal with one of those. So definitely keep them in mind. So let's try a little bit more practice here. Problem 5. The antiderivative, or the integral, of 1 divided by x minus 1. Well, I think if you ignore that minus 1, this to me looks a lot like 1 over x. Thinking about this function that we're finding the antiderivative for, and this is a little bit of a sidetrack, but we'll come back. It seems like to me that the domain of this function is x is allowed to be every number, right? Nothing's going to break this fraction except 1. I think 1 would break this fraction. And if I'm going to put an equal sign here, then whatever this is equal to better have the same domain. So let's take a look. No integral this time. I think just 1 divided by x makes you think this will probably be natural log. Then hopefully you'd try, well, is it just x minus 1 plus c? And you're honestly super close. If you were to take the derivative of this to check it, natural log of x minus 1, this would indeed be 1 divided by x minus 1 times the derivative of the denominator, which is just 1, so we don't really even need that part. And so you're looking pretty good, and you're like, haha, I did it. That was not too bad. But you're not quite right, because the domain of this function is the domain is x is greater than 1. And that means that it is x not equal to 1. X can't be 1 because we can't do the natural log of 0. But it's also x can't be less than 1. And so those domains do not match. How do we make them match? Well, the reason that x can't be less than 1 is because then the interior of the natural log becomes negative. And we know we can't do natural logs of negative numbers. But we know how to turn something from a negative to a positive. Couldn't I put absolute value around this? And then I'd be allowed to use a number like x equals 0 or x equals negative 1, because when we plug those in, the inside becomes negative, the absolute value acts upon it, turns it positive, and then you can do the natural log. But then, wait, how do we check that derivative? Is that still the same? Well, we work this same piece over here, and it becomes the natural log absolute value x minus 1. How do we do the derivative of absolute value? Well, in the past, we've really had to draw a graph, but we did discuss briefly with natural logs and said we'd revisit it this semester, that if it is the natural log of the absolute value, then the absolute value actually disappears. And so now we get to kind of come full circle, where in first semester it's like, this isn't super important, something you need to keep in the back of your mind. Well, now it is very important, because if you go to do the antiderivative of something that ends up with a log, natural log or regular log, you must include your absolute value, or by putting an equal sign, that is not a true statement. They would not be equal if you didn't have the absolute value. So you must have that. You don't need to give the domain, but here are our matching domains at this point. And so we do need the absolute value every time we have log or natural log. All right, problem 6. Let's see, e to a power. Ooh, well, I think we might remember that e to any power, when you take the derivative, stays itself. So shouldn't the antiderivative pretty much be the same? Let's try that. Let's see if it's 2e to the 2t plus c. Well, checking this really quickly, taking the derivative, this time with respect to t. Notice this dt is telling us what variable, so we're going to do 2e to the 2t. This becomes 2, stays the same, it's multiplying e to the 2t, oops, times an extra 2. Drat. So this would actually become 4e to the 2t over here, and doesn't quite match, but it is very close. I think in order to turn a 4 into a 2, you'd probably need an extra 1/2 out front. And so in fact, I think this would simplify to e to the 2t plus c. And hopefully mental math wise, you can see that when you do the derivative of this, it is e to the 2t times 2 and matches where we started. So nothing too bad, just remembering that chain rule. It's going to bite you in the butt a couple times. Speaking of the chain rule, we don't really have a reverse chain rule. We will learn a couple strategies to help you when there's that chain rule buried inside over the next few days, but I find it really helps the majority of us at the beginning just to think logically about it, bring in our idea, our concepts of the chain rule from last semester, and just make sure you're remembering when you do the derivative, you need the chain rule. So when you do the antiderivative, you need something to cancel out the chain rule. Okay, 2 to go. This one looks weird. Why did they move the dx up top? Well, I mentioned this last class, and I actually showed this a little bit earlier too. I wonder if I can find that up here. Oh, yeah. I showed this over on 4. I actually put a little times dx. Now, you don't have to put the times here, but technically there is a multiplication. So there's no multiplication at the beginning, but it really means the integral of this times the differential, times dx. And we'll explain why and what this weird little dx thing actually represents and why we can put multiplication there. But we do need to realize that there is actually multiplication. And sometimes our textbook writers, again, our biggest enemies, try to save themselves some space. And so instead of, and let's see if this is the same thing, if I put a negative 1 over x times, and we'll write the dx up here to make it clear. Instead of writing something like this, they say, well, dx is over 1. Let's just multiply straight across and rewrite it using a little bit less space. And so we need to realize that if there is that dx moved around, not at the end, I always prefer to move the dx out to the end, and we end up with something like this. Of course, that was just notation. We didn't actually do the problem. So you're looking at this and you're like, okay, well, let's take that antiderivative. Well, if we take that antiderivative, hopefully you're already thinking natural log, and you'd be right here. So you might think, well, there's a negative, so is this the natural log of negative x plus c? And notice I got that absolute value. Let's find out. So if I do d dx of this guy, okay, absolute value again is going to drop off 1 over what's inside times the derivative of what's inside gives us, oh, that's weird, right? This actually gives me negative 1 over negative x, which is 1 over x. That didn't work. That's strange. Well, how do we get it to match then? And the answer for this is just a small little trick. We need to realize the same way as when you're taking the derivative, let's say I had a 4 here, and I said, well, I don't want to think about the 4, I want to factor the 4 out front. Well, we can actually do the same thing with this antiderivative. So before I go through all of this, what if I rewrote the problem as negative integral 1 over x dx? And then it becomes a little bit more straightforward. The negative is just hanging out. 1 over x we know is the natural log absolute value of x. And then we have a plus c at the end. And we're good. Of course, some of you might have said, well, wait, no, there's another way we could do it too, isn't there? Couldn't we have also said that the answer is negative natural log? Well, actually, let's do it as we did before in red over there. So it's the natural log of negative x plus c. Because you might have noticed that this answer over here, like that answer is really close to what we started with. It's just missing a negative. So can't we just put an extra negative out front? Sure. That's totally fine, because you notice if you do the absolute value of negative x and the absolute value of x, you will actually have the same graph. So either one of these are correct. They will mean the same thing. Totally up to you about how you think about it. All right, you guys are getting pretty good at this now, so why don't you go ahead and pause the video, try problem 8, then we'll explain what you're working on for the rest of the day. All right, well, hopefully you've unpaused and you have an answer for me, so let's look at a couple of the answers you may have come up with. All right, so antiderivative of e to the x squared. You're like, I got this. E to the x squared never changes, so I think it is e to the x squared. Oops, plus c. Cool. Well, then I challenge you. I say, okay, well, let's take the derivative and make sure you're right. So the derivative of e to the x squared is itself, oops, can't forget that chain rule. The derivative of x squared is 2x. And I believe that this does not match what's up there. So drat. We're like, oh, there's an extra 2x there. No good. Didn't work. So what if instead we tried to cancel out that 2x? We're like, oh, I don't like that 2x. So let's do a 1 over 2x times e to the x squared. Because then you're like, well, now when I do the derivative of this, I'll get this guy. But then there's a 1 over 2x out front that will cancel out the 2x at the end. Okay, well, let's check it. D dx of, in fact, why don't I rewrite this really quickly? E to the x squared over 2x. I'll space save this time. Textbook lovers everywhere love me. And we do the derivative here. But wait, to do the derivative here, don't we need the quotient rule? Oh, I guarantee when we do the quotient rule, there is no way whatever this is matches this nice little guy over there. So what are our other options? And in fact, this is something in Calculus AB that we cannot find the antiderivative of. It looks super simple. It seems like it should be an easy answer, but it turns out it's not. In Calculus BC, you'll learn a concept called infinite series. And with infinite series, you'll be able to write out an infinitely long function that is the antiderivative of this. But without knowing that infinitely long function, there is no simple function where when you take the derivative, you get e to the x squared. And that's pretty astonishing. Again, it's very different than derivatives last semester, where we could take the derivative of any function we wanted. With antiderivatives, that's not the case. There's only a small class of functions where we can find the antiderivative, right? For example, up here, you guys found the derivative of secant squared, no problem. But if I asked you to find the antiderivative of tangent squared, you might be in a world of hurt. I don't know a nice, easy way to do that, unfortunately. And so we need to realize again that although the majority of problems that you see should have an antiderivative defined, and in fact, pretty much all of them, unless I come up with them this semester, you will be able to find an antiderivative. As a whole throughout calculus, there are many functions that will need other methods to find antiderivatives for. And there are some, like this crazy guy down here, that there is no nice antiderivative. So what are you doing for the rest of today? I have 3 riddles for you, and they are silly calculus riddles, and part of the fun is understanding why the answer to the riddle is funny. And so you may have to do a bit of a deep dive to understand why it makes sense first, right? You're looking at this crazy thing, you're like, what is happening here? And you're going to get an answer to it down at the bottom, and even a translation, but you will need to explain how they get there and why the answer is funny. Now, in order to do it, it's nothing too terrible. You take a look at the first part. There's no calculus needed for 1 through 10. You're just trying to match one of these to one of the letters down below, right? You might take a look at this guy and say, oh, this is the one. This is 2x. Let's see, the 5 stays below. This 2 comes up. This is 2x to the 2/5. Where's that? Oh, that's t. So we know that 3 is t. Where is that? Right here. Cool. And you probably don't need too much work there. Nothing terrible. However, the second part is where the calculus comes in, right? Part 2, we have 10 more questions, and you actually need to find the antiderivative. Now, on some of these, you probably don't need too much work. For example, 13, hopefully at this point, you could say, oh, that's 1/3 x cubed. And so you look for that 1/3 x cubed, and you say, oh, 13 is d. Very nice. But on others, you will probably need to show at least one step. And in fact, on 11 through 20, I am going to ask you to write out each of the problems, 11 through 20, and then any steps you need, probably 1 to 2 steps to get to the answer. Right? If you're doing 19 and you skip right to the answer, I'm going to be really impressed or a little bit suspect. Right? On 19, I'd probably show some work that looked like this. Okay, we have this guy remembering that dx. I'm going to rewrite this first. How would I do that? Well, I see this 1 over 2. I'm actually going to factor out the 1/2, and then 1 over the square root of x. Square root of x is x to the 1/2. I'd probably bring that up, x to the negative 1/2. And then I'd take that antiderivative, ignoring the 1/2. So we'd add 1 to the power. Negative 1/2 plus 1 is 1/2. What cancels out a 1/2? That's a 2. And then we might see that these guys will cancel, and x to the 1/2 is the square root of x. There we go. I had to show a couple steps. I assume that you guys will as well to get to w. So, showing a few steps there, it's nothing terrible. You don't have to rewrite the whole page, just a few problems. The second riddle goes a little bit faster. It incorporates both integrals and derivatives, just to keep you on your toes, so be ready for that. And again, trying to show any work that is necessary would be great. And last but not least, riddle 3. You'll notice that the second one deals a lot with exponentials, which should make sense then that the last one deals mostly with natural logs. I do have the complete solutions posted on Microsoft Teams for you, but I wish you the best of luck. I'm sure you'll do wonderfully. Thank you for tuning in, and I'm excited to have you back next class for day 64.